up an even longer standing Embedded Vision Summit presentation veteran. This is Amol Borkar, Product Marketing Director of Cadence. Title of his presentation is Addressing Tomorrow's Sensor Fusion and Processing Needs with Cadence's newest processor. And I'll give you a quick preview of one of the things that we're going to talk about in Q&A. He's going to talk about sensor fusion. There's also this term called multimodal. And so we'll explore, maybe he'll touch on it in the presentation, but we'll explore a little bit more in Q&A, whether those terms are the same or different or kind of the same. All right.
Thank you, Brian. All right. Okay, good afternoon, everyone. Thank you for being here. I'm Amol Borkar. I'm the Director of Product Management and Marketing at Cadence Design Systems. And today we'll be talking about our newest Cadence DSP processor. So let's start first with the market trends. So if you look at various of these segments, we've got AR, VR, automotive, IoT, data center. One of the common thing over here is all of these markets use sensors. But what's happening over time is the number of sensors required is on the increase. And we're not just talking about vision sensors, considering this is Embedded Vision Summit. We're talking about a combination of vision, radar, LiDAR, time of flight, event sensors, what have you. And while the number of sensors is increasing in all these markets, we'd like to focus a little bit on automotive because that's where we're seeing a big uptick in the number of sensors being used. So here's a look at a slide that we borrowed from Yole Group, and it basically shows that the automotive industry is heading towards self-driving and autonomy, and you can see the number of sensors on the vehicle is on the increase. Back in the day, we had just one camera looking at the front of the vehicle, but now we've got sensors looking at the front, back, left, right. You've got A-pillar sensors, tailgate sensors, proximity sensors, parking sensors, hundreds of sensors around the vehicle. And that number of sensors is rapidly on the increase. In this case, you can see this is over 40 sensors. But we expect this number to grow even more as you get more towards level 4, 4+, or 5. So one way to segment the automotive market is to look at, traditionally we had a lot of edge and domain-based controlling happening, and that was typically done on ASIC and ASSP implementations. Now, as the market has evolved and we're starting to see more digital cockpit and infotainment systems, we're starting to use more MCUs and CPUs. And the next generation, once we're starting to get into really, really heavy compute, we're starting to see a lot of applications on the central compute or the central SoC. And there's obviously a big drive for this because if you look at the different types of compute modalities that are being used in the vehicle, right here you can see we have a bar chart going from 2023 to 2030, and we've got various different blocks by the different legends. You can see they're all on the uprise, right, on the uptick. The MPUs are growing at about 9%, central compute is growing at about 30%, MCU and special logic is growing at about 15% as well. But the main takeaway from this is there's going to be a lot of evolution in the different types of compute modalities that are going to be provided, but it's finally, the customer is going to choose the right platform that they want for their solution, and want to try to have sort of like a common architecture that can be scaled and used across different application segments. So looking at the automotive market trend, we can see there is, interest or growth in a number of things. So you can see the number of sensors is increasing. As we mentioned, the different types of sensors. You've got 4D imaging radars, cameras, LiDARs. We're looking at sensors looking both outside the vehicle, inside the vehicle. These automotive vendors are primarily looking at pushing the car to having, a mind off, eyes off type of solution, so the car can drive itself. In this case, we are looking at this ADAS and IVI, or the in-vehicle infotainment type of capabilities, moving to this central compute, as we mentioned. This will obviously require heterogeneous compute using different type of modalities, or as Brian said, multimodal processing or multimodal computing and sensor fusion. And last but not least, also, the car is starting to become like a computer or a smartphone. We're starting to see a lot of these SDVs, software-defined vehicles, starting to become more and more prevalent, if not now, at least in the next 5 years. So let's take a step back and take a look at some of the places where we are seeing a lot of evolution. So if you look at the radar space, for example, we started with 2D radars. Now we've gone to 3D radars, 4D radars, 4D imaging radars. We've got all this type of compute available that gives you very high precision, point cloud-like detail from a radar. You combine that with a camera, use that with the central ECU for computing, and all of a sudden you've got now your sensor fusion or your multimodal processing, which is being used in a lot of applications today. It is 2024, so we have to talk about AI, but what we want to call out over here is very simple. You can see back in 2014 when a lot of the AI started kicking off, we were starting to see things with the hog-based approaches, hard classifiers, pattern recognition approaches. About a few years after that, we started seeing the movement into CNNs, RNNs, LSTMs. And then in 2018, 2019, the big boom, right? We started seeing transformers. We started seeing the language-based transformers. Now we're seeing vision transformers. Next, we are seeing Megalodon and all these different types of crazy names of things coming out. But what we're trying to point out over here is the timeline below it, right? There's a rapid evolution of all these modalities coming out. And the takeaway from this is that the AI front is moving at a very fast rate. But we want all this AI to run on silicon that we have, whether it's a hardware block, whether it's GPU, NPU, whatever it is. It means that the silicon also has to evolve at a really fast rate. But unfortunately, silicon, as we know, has a lengthy design cycle or a development cycle. So if you freeze a design today, you need to be able to address the market requirements 2 or 3 years down the road. Otherwise, you're going to have a fancy piece of silicon which you really can't use. So need for future readiness in a rapid evolving AI world is very critical for most future applications. So this brings us to sensor fusion or multimodal processing and why it is important. So first question, simple, is what is sensor fusion? It's basically taking information from maybe one or more sensors. Could be cameras, could be radars, could be multiple cameras, multiple radars, cameras plus radars, whatever have you. For example, you also have it on your own human body, your 2 eyes, looking at the same thing but from a slightly different perspective. You're doing some sensor fusion over there to get a better understanding of the world. Now, the question is, how does it help? Well, simple. There's some redundancy element over here because if one sensor fails, the other one can compensate, but they can also work together to give you better quality, better fidelity of the environment. So you can utilize each sensor's strength to minimize the weakness and basically have a larger coverage. Also, going from sensor fusion, which is more of a classical approach, augmenting that with AI can probably be the best combination. So some common sensor fusion examples that I'm sure most of us know is 3D depth perception using 2 or more cameras. You have also improvements to SLAM, where you have a camera-based localization and mapping. You can augment that using an IMU or using more cameras. Using cameras and radars in ADAS or automotive applications. Excuse me. And then cameras plus radars plus LiDARs plus AI to make the solution even more fortified and stronger. So these are just a few examples, but obviously there are a lot more out there. Now if you look at a typical perception system, you can see that an SoC architecture may not be exactly like this, but has many of the common elements. You have domain-specific DSPs, you've got accelerators, you've got NPUs, GPUs, hardware blocks, interconnects, NOCs, etc. But what we're trying to point out over here is you have so many sensors feeding in data into this compute block, and there are different types of processing that is required, right? Because the GPU has different processing, NPU has different processing. So the need for heterogeneous compute probably is very important. But scaling at heterogeneous compute can be difficult because if you've got all these different blocks, having different architecture, reusing the code can become a big hurdle because today you're on one generation of product, moving to a different architecture for a next-gen product can be a big step to take, but it is the world we live in, so we have to figure out some way of how we want to solve that problem. Which brings us to the race towards the central compute. And what we mean by that is, if you look at a vehicle, traditional vehicles or typical vehicles today are more on this domain architecture. Excuse me. So you have domains for compute, you have domains for connection, you have domains for audio, et cetera. And what we're starting to see is this move towards the central compute, where you have a main CPU that is doing a lot of the processing, and then you have this zonal architecture or zones where the sensors are processing, sending the data in over high-speed SerDes or automotive Ethernet, and then coming to the central compute for processing. So obviously, as we improve the technology nodes, we're getting faster compute, we're getting faster processing, lower power, lower leakage. But manufacturing costs go up. You're looking at typical 3 nanometer mask set, it's about 20 million. It's not cheap. So not everybody can afford it, and then also does not allow you easily to do respins if you need to make changes to the design. So scalability is obviously very important. And the idea with scalability over here is, can I get more out of my IP? I've put all these IP blocks in my SoC. Can I do more than just one purpose-built function, right? So if you look at an SoC over here, what we're trying to show with these different color blocks is you've got different compute units doing different things. But this obviously has a problem with scalability, as we pointed out, because if these things have different architectures, if they have different ways of processing, different programming languages, then if you want to gain performance, you want to add more blocks, you want to make multi-core, not very easy to do it. But what we're starting to see is customers moving in the direction of, can I have a little bit more general purpose or something that is capable of just doing one purpose-built function, and that way I can instantiate multiple instances of those. If I want to have more performance, more performance throughput, more capability, I just put more instances or make multi-core solution from it. So for that, we fortunately have an answer for you, and this is with our new Tensilica Vision 341 and 331 DSPs. So these are targeted for high-performance vision, radar, LiDAR processing. So they are new 512-bit and 1024-bit machines, as we mentioned, targeted for vision, radar, LiDAR, AI, sensor fusion, multimodal processing needs. So architecture is very similar to our previous generation of products. And the good thing is we have taken our very successful Connex DSPs, which are great for radar communication stack, and then our very successful vision DSPs, married them together, provided an enhanced ISA that can allow you to do all this processing on one IP very efficiently with the best PPA and best performance. So the good thing about it is our vision DSPs were very successful, so all the goodness we got from there made it better and brought it on the next products. So just a snapshot of a few of the highlights about this product. So obviously we've added more data types, more support. We've added improvements to computer vision filters. 1D and 2D filters have significantly improved support or added support for nonlinear operations, both fixed point, floating point, improved support for fixed point and floating point FFTs, both complex and real FFTs, as well as support for AI as well for the depth-wise separable convolutions and some network quantizations. Best of it all is not just the silicon that we have improved, but then all the libraries, all the tools, the SDK, everything that we had for our previous gen of products, we brought them in on this product as well. So if you're working with our previous products, whether it's the Connex products, it's the Vision products, you can bring it over very easily to this new product and be up to speed, running at 60 miles per hour from the get-go. Aside from the Vision DSP, we also want to announce our Vision 4DR accelerator. So this is a specialized FFT accelerator targeted to do high-performance 1D and 2D FFTs in 16-bit and 24-bit. So this is meant to be a co-processor, partners with our Vision DSPs that we just announced, the 331 and 341, and it is also automotive certified, or will be automotive certified. It's going to be coming out very soon. So just like the DSP, great for automotive solution. And in terms of performance, it's also really good. Compared to the DSP itself, we have about 4 times higher performance on this accelerator for FFT capabilities. And then performance per area, you're seeing 6x or higher. So if you are going to be processing some really large data cubes for 4D imaging radars, this is a very good solution for you. Sits on an AXI fabric and works very nicely with our Vision DSP. So if we relook at how the sensor hub can come together with these new products, you can see the SoC architecture can be reimagined a little bit, because now you've got a couple of instances of vision DSPs. You are not limited to one. You can put multiple of them, because our DSPs play very nicely in a multi-core fashion. You can put multiple instances of the 4D accelerator as well, and then also pair with that our Neo NPU, which is a high-performance neural engine NPU processor for running the multiple tops for your latest AI workloads. So this way, you can see multiple of our Tensilica IPs can be put into an SoC to meet your application needs. A simple example of how this sensor fusion could be working with our new vision DSPs as well as our previous generation of products. So you have a radar heads feeding into our new vision cores. You have the CV processing on the camera heads, which are feeding into our CV DSPs or our previous generation of DSPs. The output of that can be combined either with early fusion or late fusion going into our NPU. And obviously, like all NPUs, they're not bulletproof. So for the layers that are not supported, you can see a feedback loop being sent back to the DSP, which is why the DSP also is very essential in a lot of these AI solutions, because the NPU can support a lot of layers, but for the layers that are not supported, you can pump them back to the DSP, get them to run efficiently, and then send the result out to your application. So the takeaway from this is now you have a single DSP that can target multiple sensor modalities very efficiently, easily, pair with our NPU as well for a very high performance classical plus AI processing workload. So our software stack is also quite comprehensive. We have been evolving on this software stack for a number of years now. We support standard C++, OpenCV, OpenCL, Halide, and then the neural net approach using Onyx, TVM, TensorFlow, PyTorch, etc. And then we have all the supporting stacks in between. We have the OpenCV library, SLAM library, fundamental math library, Simulink, radar libraries, everything that you need for today's and next-gen application SDKs. So a quick recap of our announcement, which we did in September of last year. So this was the announcement that showed that we have a very high performance, high PPA, and high efficient NPU, which also can be used for automotive applications and can pair with one or more of our Tensilica DSPs. And then we also have a NeuroWeave SDK, which is a neural network compiler, which is a very nice tool, which is on its third generation of product. So we've been developing this thing from 2017 or 2018, and now we are able to take several hundreds of models from the model zoo, very efficiently run them on our preferred targets, whether it's the DSP or the NPU targets. You can consume TensorFlow, PyTorch, Caffe2, Onyx, MXNet, or if you've got pre-quantized models also, that can be easily consumed by this network as well, by this compiler, and then you can specify your target. You want to run it on the DSP, you want to run it on the family of DSPs, you want to run it on the NPU. All of that works the same. And it's meant to be a scale solution, so we are able to support running the very, very small, tiny ML type of networks, which are used for always on, as you can see, with the few GOPs, all the way to large segmentation models, transformer models, ADAS, etc. All the same software that can be used across all the different products that we have. So if you put it all together, basically we've got a variety of solutions for different modalities that you want to process. So if you're looking at just radar processing, we've got our communications, our Connex line of products, which can be used to go all the way from base level processing all the way to what we call turbo high level processing. You want to combine vision and AI, we've got a family of products for that. You want to do vision plus radar plus AI, we've got our new Vision 230, Vision 331, Vision 341 products, which are just announced. Pair them with the radar accelerators as well as the Neo NPUs, and you just have a whole range of applications you can target. You can go all the way from the 2D radar applications all the way to the 4D imaging radars, level 5 applications, military applications, occupancy sensing, all of that. So you're not just processing one big workload, but a variety of workloads using a multi-threaded fashion as well. So with that, just to recap, basically, as we mentioned, automotive market is evolving and the SoC architecture is moving into this more software-defined programmable approach. And having a solution for that is obviously very critical to your success. We announced or we showcased our Vision 331, Vision 341 DSPs, which is allowing you to process, both vision, radar, LiDAR, multimodal type of processing, both in the classical sense as well as the more deep learning sense, allowing you to consume those type of networks as well for early, mid, or late fusion. We have a very strong software ecosystem with partners and libraries that is carried on from the previous generation of products to this new product. And then we also showcased our Vision 4DR accelerator, which is great for very large data cubes of FFT and radar processing, which can be paired with our DSPs for high performance throughput. So with that, I'd like to thank you for your time, and I'll open the floor to some questions.
Applause for our presenter.
Do I go to the next slide? Oh. And last but not least, I was going to say I also have an intro talk on SLAM tomorrow at 4:50. It's the second last slot, so I hope people are there, but it's a more high-level talk, introduction to SLAM for new program managers or product managers who want to get a gentle introduction with, without getting too technical about the main terminologies behind SLAM, how it works, and how it can be used in various applications.
You just ruined my joke.
I'm sorry. Let's rewind one minute back.
No,
I
what
apologize
I was thinking I was going to say as I went up the stairs is, I'm sorry, you have 15 seconds left on your presentation. You have to keep talking. And then you proceeded to keep talking. So I'm sorry, you're over time. That's all right, just a little bit.
Apologize. You can write me a ticket.
Audience questions at the microphone. Anyone? We got about 5 minutes. Anyone? All right, I'm going to start then.
I think
oh, you got one?
Yeah.
All right, no,
yeah,
you first.
For the new Vision DSP, right, the 3.1 and 3.41, I see that you mentioned the B-Float 16.
Can you come a little closer to the mic?
Yeah, for the new Tensilica 3.3.1 and 3.4.1, I see you listed the feature, the B-Float 16.
Yeah.
And also the complex flow support.
B-Float 16.
B-Float and the complex flow.
Complex, yes, yeah.
Are those for? I presume that they're not for the neural network acceleration type of thing. There.
Those highlights were. So the question was basically, if just to recap.
What are they used for, basically?
Yeah. So what was their use, or what they're being used with?
Right. What are those two features used for?
Oh, so let me see. You said B-Float 16. Oh, complex floating point. Obviously, we see for a lot of imaging radar or radar type of applications.
Like FFT, those type of things? Like FFT?
Yes, yeah. And customers obviously are within the range of some customers like fixed points, some customers like floating points, some customers like fixed and floating points. So we don't want to be, squeezed into a box in one place. So we are providing the comprehensive support both on the fixed point implementations as well as the floating point implementations.
So both the BF16 and the complex are for those purposes? For
the complex float, yes. BF16, it's a little bit more case by case right now. We're seeing a lot of customers using it on the learning side. A few customers have been using it on the inference side, but it's case by case, so we're not seeing a full holistic use of it at the moment right now.
But is the Vision DSP designed for the neural processing?
Is the Vision DSP designed for neural processing?
Yeah.
So question is, we do support it. So obviously, compared to an NPU, NPU is going to be far more efficient. But the DSPs that we have, very configurable. So depending on how much workload you want to run, you can add or remove the number of Macs that you want. Plus, we have different options over there to assist those Macs. So we have specific ISAs also that can help in some things to accelerate your depth-wise convolutions or some of the quantization layers that are required and some of the scaling. It's if you had asked this question about 5 years ago, obviously the DSP was the core processor that was there for neural networks. Now we also have our Neo family, which does the AI processing very efficiently. But then the DSP sits as a complement to it because, as you know, NPUs, whether it's ours or whether it's yours or it's anyone else's, they're fixed function blocks, right? So today you design it, you're working with transformers today. 3 years later, you come to run Transformers 2, and there's a number of layers that are not supported on your NPU. Your whole system cannot shut down, right? You have to run the things on the DSP. So that's where the DSP comes in. And we add some ISAs, obviously, to provide some performance enhancement, and the rest of it stays programmable. That can be just done from
So
software
on the
updates.
Neo side, are those two data types support as well?
That let's talk offline, but like we have mostly focused on the fixed point implementation on the NPU. We have some floating point, but mostly fixed, because you get maximum vector processing from just doing int 8 or int 16, right, for your performance throughput.
Right. Okay. All right. Thank you.
All right, thank you. All right, for my question, I'm going to have a visual aid. Where's the slide that had the O group graphic on it? It's toward the
Keep
beginning.
going.
All right, you know it better than me. Tell me when to stop.
Was it that one or?
The one that had, where you talked about automotive applications. That one.
Okay.
Ladies and gentlemen, this is the visual definition of a processor developer's dream. Look at all that data. Look at all those different sensors. Look at all those different types of sensors. Look at all that data that needs to be crunched. Therefore, explaining why you're showcasing this application in your presentation, totally understood.
Yeah.
Are there other related, like autonomous things applications or applications outside of autonomy that are also on your company's radar? You know, I'm thinking like from an autonomy standpoint, static and mobile robots, aircraft, drones, etc., watercraft, other things. What else gets you excited when you look at potential markets and applications?
Yeah, so good question. So I think there's two parts of it. Obviously, there's the business part of it, and then there is the technical part of it, right? So we are IP providers, and obviously we like data. So as much data as we can process is great. So all those segments that you mentioned, whether it's drones, whether it's mobile phones, whether it's robots, the UAVs, the tractors that can go, the John Deere lawnmower that can mow itself and everything, that all is very applicable, and it can all be used. Now, the business part of that question comes up is where we are focused on is the guys who are building the chips, because automotive right now, as we are seeing, there's a lot of OEMs and tier ones coming out that are building the SoCs for your SDVs or pre-SDVs. So we're seeing a lot of silicon going in there, and it's not just your one or two guys that are building the silicon. Now, if you go to China, where I'm focused quite heavily on, every corner there's different guys who are building their own silicon. You've got Horizon Robotics, you've got Black Sesame, you've got BYD. All of these guys, not just the OEMs, but they're also building the silicon, right? So there's a lot of play over there. The problem that we've typically seen in this drone and robotics space is it falls in the IoT bucket. And from my experience, it's more of a sum total game, in the sense that you're not going to be having 5 or 6 vendors who are building 100 million units. It's going to be probably 100 guys building 10,000 units. So for them, building their own SoC doesn't usually make sense. So they're usually buying off-the-shelf components for maybe some of the sensors they might make their own, but the building the main SoC is usually quite expensive, right? Whether you're looking at 40 nanometer or even higher technology nodes, it still doesn't give enough ROI to go build your own silicon. So buying silicon from somebody else probably makes sense for them. So what we do is we sell to that person who they buy from. So we make sure that they are on our roadmap. So may not be directly addressing that drone or market segment, but
it's a very small drone, by the way.
Yeah. So we indirectly support it. So we make sure that the customer that we are providing the silicon, the IPs to, they, in some cases, they have a plan of addressing all these IoT spaces. So we are able to benefit them as well, and they benefit us as well.
Okay.
Does that answer your question?
It does, very much. We're out of time. Round of applause for our presenter.